Okay, we'll continue on with our discussion of learning the rules to calculate theoretic probabilities. Okay, so theoretic probabilities, again, these are probabilities that are based on kind of these mathematical rules. We've learned the rules for calculating the combinations of events, probabilities of A or B. Okay, and now we can talk about when we have associations in events. Okay, so I'm going to copy this table about. Actually, let's copy this table here about the cat and the dogs. Okay. All right, so this is our information that we have about someone owning a cat and someone owning a dog, okay? And we can have what we call givens, okay? Given probabilities. So we have something called conditional probabilities. And we would read something like probability of A vertical bar B. This is read as probability of A given B, okay? And this is basically saying what is the probability of A if we know B has happened. Okay, so this is different. This is not probability of A and B. It's the probability of A given B. All right, so we could say probability of cat given dog. This is what is the probability someone has a cat if we know the person has a dog. Okay, so probability of cat given dog. Okay, so what is this? How many people qualify? So we're limiting, basically, as soon as we say if we know the person has a dog, we are essentially limiting ourselves just to this column here. Okay? If we know the person has a dog, we're limiting, this is our world now. Okay? Everything out here, it doesn't matter. So now, looking at just the people who own a dog, the probability that someone has a cat is going to be 22 out of 40. .55. Okay. So if we know someone has a dog, the probability that this person has a cat is going to be 22 out of 40. Is that okay? All right. What is this? What is this thing asking? This is, what is the probability someone what? That someone has a dog if we know the person has a cat. Okay. Can we, do we see the difference here? Okay, and then so what am I limiting myself to in this question? Yeah, we're limiting, as soon as we said if we know the person has a cat, we're limiting ourselves just to this row here. These are the only people that now matter. Okay? So in the denominator, I'm going to put what? 35, and in the numerator, I put 22. Okay, and so my answer here is 22 over 35, and that's 0.629. Is everyone good with this so far? Okay. Let's continue working with this. All right. There's this question of, we have something called independent events. Okay. Two events are independent if the outcome of one event has no influence on the outcome of the other. Two events are independent if the outcome of one event has no influence on the outcome of the other event. So, you know, if we have two coin flips, those are independent events. If I get heads on the first coin flip, it has no influence on the next coin flip. Okay? And so we could ask, is owning a dog independent of owning a cat? Okay. And you know, don't get caught up on what it means to say this thing has influence on the other, okay? What we want to know is just from a statistical perspective, is the probability of owning a dog or cat influenced by whether or not the person already owns the other animal? So is the probability of owning a dog, is that influenced if we know this person has a cat or not? Okay, that's what we want to know. Okay, so is owning a dog independent of owning a cat? We want to know, basically another way of asking this is, if a person owns a cat, does that affect the probability that this person has a dog? Okay. And so if they were independent, if it does not affect, okay, so if cat ownership and dog ownership are independent, then what we expect is that probability of dog given cat. So what is this saying? The probability that someone owns a dog if we know the person owns a cat. This should be the same as just the probability that the person owns a dog, whether or not we know the person has a cat. So whether or not, if we know the person owns a cat or not, that should have no effect on just the probability of owning a dog, okay? Or another way, that the probability of owning a dog, if we know he has a cat, this is, this would also be equal to the probability of dog given no cat, okay? All of these things would be equal to each other. They're all equal to just the probability of owning a dog, okay? You just have to check one of these things. So I'm just going to say probability of owning a dog given cat, is that equal to the probability of a cat? Okay? If these are not equal, then they are not independent. Okay. Do we understand? Does this make sense? So we could say, let's say being left-handed is independent of owning a dog, okay? So if that's the case, we could say, what's the probability that someone is left-handed? Maybe we say 15%. There's a 15% chance that a person is left-handed, okay? I could say, oh, wait, hang on. What if I told you this person owns a dog? What's the probability that this person is left-handed now? You'd still say 15%, okay? Because owning a dog is independent of being left-handed, okay? On the other hand, if I said, what's the probability that someone is left-handed, okay? We could say, before you know anything, the probability that a randomly selected person is left-handed is 15%, okay? And we could say, well, hang on a second. This person writes with his left hand, okay? What's the probability that this person's left-handed now, okay? Well, you would say probably like 99%, okay? I mean, there's a possibility that the person writes with his left hand but is actually not left-handed or something, okay? But if you know the fact that the person writes with the left hand, then that definitely changes the probability that the person is left-handed, okay? So this is what we want to know. Is the probability of dog given cat, is that the same as just probability of dog overall? Okay, so this will, so to check, what is the probability of dog given cat? And what is probability of dog? Okay, so dog given cat is what? Yeah, we did 22 over 35, and we got 0.629. And what's the probability of dog overall? (40 divided by 100? 0.4? Yeah? Okay. So these two numbers are not equal. Probability of dog given cat is not equal to the probability of dog. Therefore, they are not independent. So owning a dog is not independent of owning a cat. Okay? And what it appears is that, if we know nothing about the person, the probability that he owns a dog is 40%. If we know that the person owns a cat, the probability he or she owns a dog goes up to 63%. Okay? So does the reasoning there make sense? Yeah. Okay, so let's try an example here for you guys to work through. Okay, and we'll say owns a bike, no bike, and we'll say owns a TV versus no TV. All right, so let's say I'm sorry, give me a second here. Do some math here. Okay. Okay. All right. This is one question, but here to help you figure this out, figure out probability of bike, probability of TV, probability of bike given TV. What's probability of TV given bike? Okay, so find these four quantities and then answer this question, yes or no. Okay, so looking around, a lot of you guys are doing well. Let's see. All right, what's the probability that if we pick someone at random, what's the probability that someone owns a bike? Okay, we have a total of 105 people who own a bike. And how many people total in the table? 140. Okay, and I believe if we do this calculation, we would get 0.75. So that's the probability that someone owns a bike overall, if we just pick someone at random. All right, if someone what's the probability that someone has a TV? Okay, there's 120 people total who have a TV out of 140 people, and so this ends up being 120 over 140, and I'm getting something like 0.857. Yeah. Okay. All right, what's the probability that someone owns a bike if we know they have a TV? Okay, so as soon as we see the given TV, we are now limiting ourselves just to this row. Okay, these are the only people that matter for that question. So this is going to be 90 out of 120. We have 0.75. Okay, and over here, what's the probability that someone has a TV if we know they have a bike? Okay, we're limiting ourselves just to this column of those people who have bikes, and our answer here is 90 over 105, which is 0.857. Okay, so to check, we have to say, okay, if they're independent, you know, does probability of A given B equal the probability of A? Okay, and if yes, then they are independent. So we can say, well, we'll just call, is bike given TV, is this equal to the probability of bike? Yes, bike given TV is 0.75, probability of bike is 0.75. This is yes. So, are they independent? Yes, they are independent. Okay, alternatively, you could also check, does probability of TV given bike, does that equal probability of TV? And if yes, then they are also independent. Okay, so we see 0.75 is equal to 0.75, so that means they're independent, or if 0.857 equals 0.857 down here, also independent. So we can see that owning a TV or owning a bike, at least according to our data, and this, this is numbers that I made up, but according to this table, owning a bike has no influence on whether someone owns a TV, and vice versa. If someone owns a TV, it has no influence on whether or not that person owns a bike. Maybe that is or is not true in the real world, who knows, but that's what we have here. Okay, so just kind of rules to summarize it out. The probability of A given B, this can be found as the probability of A and B divided by the probability of B, okay? Or conversely, if you have a table, it can just be the count of A and B divided by the count of B, okay? Which is what we had been doing because we had the table. So we said, how many people have a TV and a bike? 90. How many people have a bike? I don't remember, 105 or something like that, okay? And okay, so that's what we have there. Conditional probabilities, okay? And then to check for independence, see if the probability of A given B is equal to the probability of A. If yes, then A and B are independent. Bless you. Okay, is that okay with everybody? All right. We have kind of a multiplication rule. So earlier, on the previous page, we have probability of A given B equal to the probability of A and B divided by the probability of B. Okay? Well, if I multiply both sides of this equation by the probability of B, I would get the probability of B times the probability of A given B is equal to the probability of A and B. Okay? The labels of A and B are completely arbitrary. Okay? So if somebody wanted to call, if somebody wanted to say bike was A and TV was B, that's fine. Somebody else could call bike B and TV A, okay? And so because they're arbitrary, we can also just flip them around and say probability of A times the probability of B given A is equal to the probability of A and B, okay? So we can also do this. Okay. So this is the multiplication rule, okay? All right. If A and B are independent, so we just went over this, then the probability of A given B, this is equal to what? Probability of A given B, if A and B are independent, is equal to the probability of A, right? Knowing whether B has happened or not, that doesn't influence the probability of A. It's just the probability of A happening. If B has happened, is just the probability of A happening. Okay, and so if that's the case, then the probability of A and B is equal to the probability of A times the probability of B. So this is true when A and B are independent. Okay, so and I think we're actually accustomed to this rule, and let me just kind of expand this. Probability of A and B and C is going to be equal to the probability of A times the probability of B times the probability of C. Okay, if A, B, and C are all independent. Okay, so for example, we can say, I will flip a coin 2 times. Okay, each flip, the probability of getting heads is equal to 0.5, and the probability of getting tails is going to be equal to 0.5. So I can say I flip it twice. What is the probability? I get heads on the first, and tails on the second flip. Okay, so this is asking what's the probability of getting heads on first and tails on second. Okay, and because it's an and, all right, we can use the multiplication, and the 2 coin flips are independent, right? So the outcome on the first flip has no influence on the outcome of the second flip. So because they're independent, we can just multiply these. This is going to become probability of heads on the first times probability of tails on the second. Okay. What's the probability I get heads on the first flip? 0.5. What's the probability I get tails on the second flip? Also 0.5. So what's the probability I get heads on the first and tails on the second? It's going to be 0.5 times 0.5. I have a total probability of 0.25. Is that okay? All right. Okay, let's try something. Okay, so let's say you have, this is a bucket, and inside the bucket we've got some marbles. Okay, so you will draw a marble. From the bucket, look at its color, and put it back. Okay, and so every time we draw a marble and we look at the color and we put it back, the amount of marbles in the bucket remains the same every time, right? And so from one draw to the next draw, the which marble we get is independent. Okay, so each marble draw is independent. Okay, so let's say the probability of drawing, we'll say a green marble is 0.3. So we'll say there's a 30% chance that you draw a green marble from the bucket. Okay? So we'll say you draw 3 marbles, or you draw 3 times. Each time you draw one, look at it, put it back. Draw one, look at it, put it back. Okay? You draw 3 times. What is the probability you draw 0 green marbles? Okay. So what's the answer here? So the sequence, the outcomes has to go what? So on the first marble, we have to get what? Not green. Okay, on the second one, we have to get what? Not green. And on the third, we have to get not green. Okay, so what's the probability of getting not green on the first? 0.7, right? What's the probability of getting not green on the second? 0.7. And what's the probability of getting not green on the third? 0.7. Okay, so I would multiply all of these together and I would get 0.343 if I did my math correctly. Is that okay? All right. We'll say you draw 3 times. What is the probability you get green, then not green, then not green? So what do we do here? What sequence do I have to multiply here? So I want green, not green, and not green. So I'm going to do 0.3 times 0.7 times 0.7, and I'm going to get 0.147. Everyone's good so far? Okay, so same scenario. Okay, we'll say you draw 3 marbles, or draw 3 times. Draw a marble 3 times. What is the probability you get at least 1 green marble? Marble after 3 draws. So what does it mean to get at least 1 green marble? So that means you got 1, 2, or 3 green marbles, right? Okay. If you think about it, there are only 2 possibilities. After 3 draws, okay, only 2 possible outcomes. We can break out all, I mean, there's lots of different scenarios, but after 3 draws, we can either have 0 green marbles, 0 green, or, and this is an exclusive or, we have at least 1 green. Is there any other possibility? You either have 0 or you have at least 1. Is there anything else? No. Okay? You're either going to have 0 or you're going to have at least 1. Okay? So, and these are mutually exclusive. You can't have 0 and at the same time have at least 1. So that means the probability of 0 green plus the probability of at least 1 green is equal to what? 1. This covers all possible scenarios, right? So if I want the probability of at least 1, I can say the probability of at least 1 green is equal to 1 minus the probability of 0 green. Is that okay? Because either, again, there's only 2 possibilities. You get 0 green or you get at least 1. Right? I gave you 3 chances to draw a green marble. If you get at least 1 green, then you're a winner. Okay? The only time you're a loser is if after 3 chances you got 0 greens. So here, the probability of at least 1 is going to be 1 minus the probability of 0 green. What's the probability of 0 green? We found that earlier, 0.7 times 0.7 times 0.7. So we have 1 minus 0.343, which means the probability of at least 1 green is going to be 0.657. So at least 1 is the complement of getting none. What is the complement again? it's when that thing didn't happen. Okay? So if you didn't get 0, you got at least 1. Okay? Are we feeling okay with all of this? You want more examples? Okay. Let's, all right, so let's say another, okay, so we'll say you draw a card from a deck. Okay, and then you replace the card so that every time you draw, it has the same probability. Okay, and then so we'll say the probability of drawing a heart is 1 in 4, or 0.25. Okay, so I'll say you are dealt, oh, I'm sorry, not dealt. Okay, so you draw a card four times. Okay, so we'll say what is the probability you get 4 hearts? What is the probability you get 0 hearts? What is the probability you get at least 1 heart? And what is the probability the last card is the first heart you see? All right. So I'll give you guys a few minutes to work through these, and we'll go over the answers in just a little bit. All right, let's go over this. Okay, so what's the probability that you get 4 hearts? So this means we have to have hearts, hearts, heart, heart, which means we're going to do 0.25 times 0.25 times 0.25 times 0.25, or maybe simply 0.25 raised to the 4th power. So we punch that into our calculator and we write 0.25 raised to the 4th power, which, here, let me change this to, we have 0.00390625. Okay. 0 hearts means we have to get not hearts. So not heart, not heart, not heart, not heart. Okay, so 0.75 times 0.75 times 0.75 times 0.75, or 0.75 raised to the 4th. And we get 0.3164. Okay, and I was walking around, I think most of you guys got this, all right? So getting at least 1 heart, this is going to be 1 minus the probability of 0 hearts. We said getting at least 1 is the complement of getting none. So we're going to have 1 minus 0.3164, which gives us 0.6836. Okay. And then lastly, what is the probability that the last card is the first heart you see? So that means we have to go non-heart, 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 and then the last card is the first heart. So we're going to have 0.75 times 0.75 times 0.75 times 0.25. Okay, so I'm going to have 0.75 raised to the third times 0.25. And that gives me 0.1055. Is that good? Good with everybody? Okay. All right, so just a quick check of your understanding here before we finish up. I just want to make sure everyone's got this okay? All right. Okay, so what are mutually exclusive events? Mutually exclusive means what? Yes. No overlap. Mutually exclusive means no overlap. Okay? Or another word is that probability of A and B is equal to 0. Okay? What does it mean to be independent? Independent events.
Because then one does not affect the other, they're not conditional.
Yeah. Okay, so independent events means outcome of one event has no influence on the outcome of the other event. Okay? All right, so here's a question. If A and B are independent, could they also be mutually exclusive? Yes? No? So think about this. Before you just say yes or no, think about what it means to be independent, what it means to be mutually exclusive.
No.
Okay, you seem pretty confident. Why do you say that?
I think no, because usually when something's mutually exclusive, you have to put one over the other. Which means that in this case, I don't think it can be independent.
Okay, and I think your reasoning is correct. All right, the answer is, could they be mutually exclusive? The answer is indeed no. All right, because if two things are mutually exclusive, as soon as B happens, the probability of A becomes 0. Okay, so what is the probability of A given B if A and B are mutually exclusive? So if A and B are mutually exclusive, the probability of A given B is equal to 0 because there's no overlap, right? Once B has happened, A is now impossible. Okay, so once B happens, A is impossible, and vice versa. Once A happens, B is impossible. Okay, whereas independence means that whether B has happened or not, it has no influence on A. Okay? Independence says, whether B happens or not, it has no influence on A. Okay, so these are saying two very different things, contrasting things. So if they're mutually exclusive, they cannot be independent. Because mutually exclusive says once one thing happens, it makes the other impossible. That means it influences the other. Okay? and it's not necessarily a cause and effect relationship when we say it influences the other, but we're saying that that the probability changes, and therefore they are not independent. Okay, if there are no questions, we'll end a few minutes early today, and we'll see you guys next week.